everyone hear me? Okay. I would like to thank the organizers for putting together a great workshop and giving me the opportunity to be here. And I would also like to offer you a disclaimer. I'm not going to give an experimental talk. It does, however, actually involve caipirinhas, so I hope that kind of makes up for it. Right. So we've had a few talks already about superpositions of causal structures, and I'm going to add to that in a certain way, but I'm going to propose a slightly different notion of what it means to have coherence between two types of causal relations. So to avoid confusion, when I use the term causal, I use it to refer simply to anything that has to do with causation, so not specifically something that is causally ordered or a mixture of different causal orders. So the direction I'm going to pursue in order to reach a notion of coherence between causal relations is to start by actually looking at ways in which you can combine causal relations between classical variables. So since it's getting close to the end, here's everything that's going to happen in the talk, sort of in a short version. Firstly, I'm going to try and convince you that even in the classical setting, probabilistic mixtures of causal relations are not actually the only possibility. So you may have something that's not a probabilistic mixture and nevertheless classical. With that in hand, it comes to detecting different combinations of causal relationships. Firstly, in a classical setting, and that is going to lead us naturally to the definition of what constitutes a non-classical mixture. And finally, to round it out, there is a bit of experimental talk at the end, talking about how we actually realized this mixture and verified it afterwards. So yeah, that's it. You can. Okay, so let's look at the classical case first. The scenario that we considered as a sort of test bed for looking at what kinds of combinations you could have is this one here, where variables A and B are causally ordered, so that you have two possible ways in which they could be related. Either they share a common cause, which we don't observe but we know it's here, or they're related as cause and effect. Now, this scenario may not be as spectacular as a superposition of causal orders. It is, however, more accessible in the sense that you don't need to worry about where your variables are in a space-time. This is very straightforward. You measure variable A at 9:15 in the morning and variable B at 9:16, and it's all very clear and simple. And since we're looking for what it might mean to have different combinations of causal relationships, this is arguably one possible place to start. We do hope to come up with a notion that we can also apply to more exotic situations later on, but as a first step, this will do as well as any other. Okay, so what are the possibilities for combining these two? Well, typical approach, toss a coin. If it comes up heads, you have a common cause. If it comes up tails, you do cause and effect. So writing this out mathematically, you might say you have these probability distributions, the ways in which B depends either causally on A or also on their unobserved common cause lambda. And if, depending on the coin, you do either this or this, you have a probabilistic mixture, which leaves another possibility, namely that for either outcome of the coin, B depends both on A and on lambda. So you have somehow a non-trivial mixture in which both causal relationships are realized at the same time. And to try and make this point a bit more persuasive, that there really is a distinction between physical and probabilistic mixtures and that you should care about it, I'm going to steal an example that Rob Speckens came up with a slight Brazilian twist. It works like this. If you order a caipirinha and the waiter actually brings you a probabilistic mixture, you might wind up with pure cachaça, or you might wind up with lemon juice. So really what you want is the physical mixture, wherein both possibilities are realized in a single instance. Okay, now I'm going to need a bit of formalism. It shouldn't be too heavy though. In the process matrix framework, the way we would represent the relationship between two causally ordered variables A and B is a process matrix over 3 Hilbert spaces. input of A, output of A, and input of B. Output of B doesn't really matter for our purposes. The representation I'm going to use is essentially similar. It goes over 3 Hilbert spaces. But what I would like to stress in this introduction of the formalism is that actually this splitting of the Hilbert space is not something uniquely quantum either. It's something you do also get classically. So let's look at the classical problem. A, B, and an unobserved hidden variable. So lambda is not going to appear. But if we're looking at how A and B are related, you might say, well, take a conditional. What does A tell you about B? Except that doesn't quite tell the whole story, because there are really 2 ways in which A and B are related. On the one hand, A influences B, but on the other hand, learning A allows you to make an inference about the unobserved common cause and thereby about B. The standard example is a drug trial. Taking the drug certainly tells you something about the odds of recovery, but you never know whether it's because taking the drug makes you get better or whether it tells you something about why you decided to take the drug, which in turn might also have implications for your recovery. In order to untangle those, you use interventions. So you make it such that this variable here becomes independent of whatever common causes there may have been, so as to isolate this branch. And then if you want, you can also observe the other version of the variable down here, which tells you about the common cause branch. In the drug trial example, this could be, for instance, you randomly assign which treatment patients actually get, whether they get the treatment or a placebo. This tells you about the causal influence, and you also observe whether they were going to take the treatment on their own. So the way to represent the relationship between A and B involves splitting A into 2 versions and writing up a conditional. Given D, which is something you can control as an experimenter, you can make predictions about B and C, which are things that the system gives to you. Similarly, in the quantum case, you can have a map which takes D as an input and gives you B and C as an output. This map may be a bit unconventional because B and C are systems at different points in time, but mathematically it works just the same. So in terms of this formalism, the possibilities we want to distinguish are, on the one hand, a purely cause and effect relationship wherein only D influences B, so that a classical conditional takes the form B depending on D times some marginal distribution on C, or in the quantum case, a marginal state on C tensored with a map from D to D. And on the other hand, a purely common cause scenario wherein B only depends on lambda. So this distribution is simply a distribution over C and B independently of D. And in the quantum case, you trace over D and prepare a fixed state on B and C. Now, as we were writing this up for publication, it turned out that there was a sticking point, which is this thing here. A convex combination of terms which are purely common cause and purely cause-effect. And we would have assumed that this was a probabilistic mixture, but it turns out that it is not, for the following reason. If you look at this term down here, you have indices J on both C and B, which means that if you were to draw a causal structure for this, it would have to look something like this. J influences both of these guys, which means that each term in the sum down here, even though it's of the form B depending only on D, so it suggests that it's cause and effect, actually J acts as a common cause here, so that this would have to be considered a physical mixture. And the only way to have a probabilistic mixture is if you have effectively a single term of each type. This is just to add some clarity, but once you've clarified that part, you can simply say, this is a probabilistic mixture. Anything that's not a probabilistic mixture, we term a physical mixture. Now, how do you tell these apart? To do that, I'm going to draw on a statistical effect, which was first discovered in clinical statistics, but which also admits a very nice version in terms that may be more familiar to us here. If you look at faculty positions, whether or not you get them generally depends on 2 factors. On the one hand, your teaching ability, on the other hand, your research ability. And for the purpose of this example, let's assume that those 2 are statistically independent in the general population. So if you look at all applicants, you're probably going to have some bivariate Gaussian distribution with a peak somewhere around here. However, if you look at the people who are actually higher than the faculty position, what happens is that since getting a faculty position depends on both of these factors, you will eliminate the people who are both poor teachers and poor researchers. So you cut out this quadrant down here. There aren't many people in this upper quadrant here either, which means you wind up with two peaks, one here and one here. In other words, those two variables become correlated, negatively correlated, but correlated, under post-selection on their common effect. This is known as Bergson's paradox. And to put it in a form that's slightly more useful for what we're trying to do here, I'm going to add a variable. So let's assume that you cannot observe a person's research ability directly, and instead you're going to use their number of citations as a proxy. In this case, you observe essentially the same effect. Under post-selection on the common effect, getting a faculty position, you find that you induce correlations between these two variables here. And that's, of course, very similar to the setting we have when talking about combinations of causal relationships. Under post-selection on B, you may be able to induce correlations between D and C, so the two versions of the other variable that you were looking at. In the classical case, this is fairly straightforward. You have a conditional probability distribution. In the quantum case, for simplicity, we said, let's simply perform a measurement on B. And for each outcome on B, we can write an operator on the Hilbert spaces of C and D that tells us something about whether and how they're correlated. Again, this is a somewhat unusual operator because it refers to two Hilbert spaces of the same physical system at different points in time. But in principle, you can simply perform tomography on these two guys, perform a bunch of different measurements on C, and a tomographically complete set of preparations on D, characterize the correlations between the outcomes, and construct an operator that characterizes the state on them. And those, yes? Yes, exactly. Yeah, and in terms of these induced correlations, you can essentially read off something about how the two causal influences here, this one and this one, are combined, or in other words, how the cause effect and common cause aspects are combined. For the following reason: if you had a purely cause effect scenario or purely common cause scenario, you wouldn't be able to induce any correlations. If you had a probabilistic mixture, then you could induce correlations, but only up to a certain strength. And the hand-wavy reason for that is that if you learn that B takes a certain value, this either tells you something about D or something about C, but you'll never have sort of perfect information about both of them. You can induce perfect correlations if you have a physical mixture. For example, if B is actually the sum of D and lambda, and you know that C is equal to lambda by virtue of this preparation here, then learning that B is 0 will tell you that D and C must actually be identical, so perfect correlations. And this means that if you see strong correlations induced by post-selection, then you can rule out a probabilistic mixture. So far, this gives you a criterion for classifying the classical ways in which you can combine common cause and cause-effect relations. But from this point, it's a small step to come up with a quantum indicator, namely, if these are quantum systems and you measure B, and then you perform tomography on C and D and reconstruct this operator, and you find that it has some type of non-classical correlations, then you might reasonably conclude that there was something non-classical about the way in which the two causal influences are mixed. I'd like to stress that this is a sufficient condition. We're not claiming to have the definitive, necessary, and sufficient condition for what it means to have a coherent combination. But I would argue that this is one case in which you would definitely say that there's something non-classical happening. Okay, and this brings me to a concrete example of how you can actually realize such a combination. So this circuit here, where you prepare two systems, one of which is A, and you measure it non-destructively, then you couple them together again and get out B, this supports both types of causal relations that we're interested in. If the coupling is local, it pipes A straight through to B, you get a cause-effect relation. If it swaps the two systems, then via this preparation down here, you have a common cause relationship. And if you use a partial swap unitary that interpolates between identity and swap, then you can smoothly transition from a purely cause-effect scenario to a purely common cause scenario, passing through other cases in between. And you can actually verify that the intermediate case, where theta is pi over 2, you will realize a scenario that does exhibit this Bergson-type induced entanglement, and therefore is an example of the kind of coherence we're looking for. So if you post-select on finding the 0 state on B, you can sort of work your way backwards and find that you get a mixture of the 0, 0 state and the singlet state. And now comes the experimental part. So the yellow part here is the preparation of two photons in a polarization entangled state. One of them then goes through a measure and re-prepare setup. The other one just goes straight through. This box here is the coupling, essentially the partial swap. And afterwards, the polarization of B is measured again, and we count them in coincidence. Now, the heart of the setup is this part here. You've got the Sagnac interferometer realizing the partial swap. You can use these window glasses to control the parameter theta that interpolates between identity and swap. And we also added, before and after the interferometer, dephasing noise with variable intensity, which allows us to transition from a quantum regime to a regime where these photons essentially encode classical information. You dephase them on a basis and essentially reduce them to zeros or ones. So it allows us to go from a quantum to a classical regime. And on the data gathered from this experiment, we evaluated an indicator of coherence. Namely, we looked at this induced state on C and D under post-selection on system B and evaluated its negativity, knowing that if the negativity comes back non-zero, then we have coherence. Now, one question you might ask at this point is, why negativity? Why not look for something stronger, for example, Bell inequality violations? The problem with Bell inequality violations in this case is that we couldn't achieve them for a somewhat technical reason. Since we wanted all the systems in our circuit to be qubits, this one qubit here, one qubit here, and one qubit here, it meant that we had to discard the other qubit, so trace over it. And if you look at the calculation that works backwards, you start with a state, with a post-selected state 0 on B and the maximally mixed state on this other qubit. And as you work backwards, you'll wind up with something that's also a mixed state on these two registers, and by extension with a mixed state on D and C. And due to this term here, we weren't able to achieve a strongly enough entangled state so as to violate Bell inequalities. If instead you allowed B to be, for example, a 2-qubit system, and you post-selected on a pure state up here, then you could actually achieve a Bell inequality violation. But that would be a bit of an odd choice, I would say, because we were talking about the causal relations between two systems, A down here, which is 1 qubit, and B up here. So it would be somewhat strange to have B be 2 qubits. But in principle, it's possible. And right, so this is the experimental data. We plotted the negativity, which tells us something about the coherence, against the phase that transitions from purely common cause to purely cause effect. And on the other hand, the dephasing probability, which takes us to an effectively classical regime. And you can see that the signature of coherence between the two causal relations decreases as you go towards the classical limit, so that's a good sanity check. But in this region right here, where we have an equal mixture of common cause and cause effect, we do actually detect the signature of coherence. And this brings me to the final slide. Just to go back over the highlights, the first important point is that you can have combinations of causal relationships in a classical settings which are not just probabilistic mixtures. You can furthermore detect when you have which kind of combination using the the Bergson effect, essentially, so looking for correlations induced by post-selection. And finally, you can realize that such a combination of common cause and cause-effect relationships in a scenario with just 2 qubits. So looking forward, there are a few questions that are still open. For one, of course, as I said, what I presented is a sufficient condition, but it's not clear yet what might be a good general definition of coherence between causal relationships, a necessary and sufficient condition. And in particular, as several other talks have presented, there are multipartite scenarios where presumably this becomes far more complex. So we don't have a clear idea yet of what would happen in that setting. Another question that intrigues me is, considering that causal relations evidently can be combined in ways that are very different from the ways in which you combine, for example, classical variables or quantum states, it's not clear what the mathematical space of possible causal relations looks like. We're pretty sure that it's not going to be simply convex, but we don't know what it will be. And of course, looking at the talks about combinations of causal orders, the question is whether you could apply this analysis to superpositions of causal orders. It's not obvious how you would do it, but maybe there is a way. And finally, on a more applied note, it would be interesting to find operational tasks or games for which this kind of coherence can serve as a resource. So if anyone has any ideas on that, I would be interested in talking about them. And that's it. Thank you. Actually, can I make one more comment before we start with the questions? Yeah. So if you thought this was interesting and would like to spend more time working on it, there will be 2 postdoc positionings open at Perimeter starting sometime between next week and next fall. I don't have much more information beyond this slide, but if you're interested, just contact Rob Speckens and he'll be happy to tell you more. Well, I think the crucial part is that you only post-select on the system B. And the ways in which, let me try and find a good slide here. I would say so, yeah. I mean, there's only so much that B can tell you about D or about C.